right, let's go ahead and start Unit 3. Unit 3 is going to cover bonding, and it's going to be Chapters 7 and 8 in your book. So let's go ahead and get started. The first thing we're going to talk about is ion formation, and this should be reviewed because we covered this a little bit last unit. Now, elements within the same group, which is the columns, they go up and down on the periodic table, they have similar properties because they have the same number of valence electrons. And valence electrons are what are involved in the formation of chemical bonds between the two atoms. So the valence electrons are the ones that are either given away or added to. Now, a chemical bond is the force that holds two atoms together. And an electron dot structure or Lewis dot structure, whichever one you call them, they're helpful to us in illustrating how these chemical bonds actually happen. Now, an atom wants a full outer energy level to be happy, and we've already discussed this before. And if the outer energy level is full, then the atom is stable, and stable makes it more happy. So let's look at some examples of using the electron dot structure to show how bonding occurs. Okay, like I said, we're going to use the Lewis dot structures to actually show how things bond. So let's look at this first example up here with sodium and fluorine. We're going to go ahead and draw their Lewis dot structures. And for sodium, there's one valence electron. For fluorine, there's 7 valence electrons. And go ahead and get your periodic table out if you don't have it, because you're going to need it throughout this video. So we have 7. Now, if you had drawn them a different way, that's fine. I drew them this way because when you're drawing bonds, you need to move the unpaired electrons to the middle. So one rule, if you want to jot down steps for drawing bonds, the first rule is move unpaired electrons to the middle, okay? So that means in the middle of the two atoms. And the reason being, you're going to see in just a second, it's because the unpaired electrons are actually what bond. So this is how we make our bond for Na and fluorine, or sodium fluorine and fluorine, okay? Now, let's look at calcium. And here we'll go ahead and put another step. Another step would be connect the unpaired electrons. All right. Now, let's look at calcium and fluorine. Calcium has 2 valence electrons. Fluorine, again, has 7. So we're going to draw those. And if you're not, you really need to be drawing these examples in your notes, because soon you're going to need to look back at something, and you'll need these to look back at. Now, remember, we're going to move our unpaired electrons to the middle. So I'm going to move my other electron right here to the middle. Now, fluorine only has 1 unpaired, so we can draw our bond there, but I still have 1 unpaired electron for calcium. And they have to have all of their pairs accounted for, or paired up, or all of their electrons paired up, because that helps them be more stable. So you can only use the elements listed. So what we do is we just simply add another fluorine, because we know fluorine has 1 electron available for bonding. So we add another fluorine, and then these 2 can now bond. Now, this shows you the formula, actually, that we're going to be learning later. So this shows you the formula. It shows you that you need, over here, 1 sodium and 1 fluorine, and that's the formula for sodium fluoride. Over here, this tells you need 1 calcium and 2 fluorine. So this, and actually, let's go ahead and learn this also. Sodium fluoride, since it's 1 to 1, it's a 1 to 1 ratio. That means I need 1 sodium for every fluorine. Over here, we have a 1 to 2 ratio, because it means I need 1 calcium to every 2 fluorine to make a correct bond. Now, let's continue and move down here with calcium and oxygen. Now, calcium again has 2 electrons, or valence electrons, and I'm already going to put them in the middle so I don't have to worry about erasing them. Now, oxygen. Oxygen has 6 valence electrons, so normally our Lewis dot structure would look like this, right? But I'm going to go ahead and erase, and I'm erasing part of my oxygen. I'm going to erase that so I can put my unpaired electrons in the middle. And every time you hear that beep, I'm sorry, it's my airliner changing pen colors or from eraser or whatever. And now I just connect the unpaired electrons. All right? Now, this means that they've got a double bond. This calcium and oxygen have a double bond, and the formula would be written CaO. And this is a 1-to-1 ratio because there's 1 calcium to 1 oxygen. Let's look at magnesium. Magnesium has 2 valence electrons, so I'm going to go ahead and put them right here. Okay? Nitrogen has 5. So normally we're going to put 2 on one side and 1 on each side to make the 5. But I'm going to go ahead and place my 3 here. Okay? Now, so we can say these 2 can bond. We're still missing 1 bond. We need something else. I can only use the atoms included. So I'm going to go down here and let's just add another magnesium. And the other magnesium is going to have 2 valence electrons again. So now I can bond there, but now my magnesium is lonely. It needs another bond. So let's make us another nitrogen. I'm going to move that down a little bit. So let's make us another nitrogen, and it has 5 valence electrons again. Normally the 3 would be on 1 on either side, but we're going to put them in the middle for easier drawing. And so now my magnesium, 1 can go there. I'm still got 2 unpaired. So now I need to add another magnesium. So you just keep going back and forth until all pairs are accounted for. I need to add another magnesium with its 2 valence electrons, and I can show right here that they bond that way. All right? Now, so this is actually showing me for my formula I'm going to have Mg3N2 because I need 3 magnesium to every 2 nitrogen. So that's a 3-to-2 ratio. So we looked at those examples, and hopefully you've gotten a little understanding of how to draw bonds and chemical bonds and how we can show those. We're not going to be working on formulas today, but hopefully that got you looking and thinking about chemical formula writing as well. Now let's look at positive ion formation. Positive ions are named cations, and positive ions form when an atom loses 1 or more valence electrons. All right, let's look at an example of when a positive ion forms, how it helps it become more stable and more happy. Now, what I'd like you to see is beryllium. And beryllium's electron configuration for beryllium is 1s squared, 2s squared. All right? Now, 1s squared, if you look, and also the Bohr model. Let's look at the Bohr model. Beryllium has 2 on the first energy level, and it has 2 on the second. Now remember, the second energy level wants 8 to be happy. And if you'll remember, 2s, the 2 right here, means that we're on the second energy level, and it has to have 2s2 and 2p6 to be happy. So the beryllium, it's easier for the beryllium to give away these 2 valence electrons right here that we've got, instead of trying to find 6 to bond with. Now, remember, let's look at helium. Helium is the last noble gas, and its electron configuration is 1s2. Okay? If beryllium gives away these 2 electrons right here that I'm circling, that means that this goes away because it gave away its electrons. And can you see it's actually the same thing now as helium? Helium and that group 18 are noble gases. They are happy because their outer energy levels are all full. So these things like beryllium once they give away their 2 electrons, can act like a noble gas, which makes them more happy and more stable. It does not mean that beryllium has become helium, because it's still got 4 protons, so it's still beryllium, but it means the electrons now are in a more stable configuration. Let's look at another example. I was fixing to close it out, but let's look at another example. And we will look at sodium. Sodium has an electron configuration of 1s2, 2s2, 2p6, 3s1. All right? Now, the noble gas right before it is neon. And neons is 1s2, 2s2, 2p6. Right? So sodium has 1 valence electron. That's right here. 1 valence electron. If it gives that valence electron away, we can cross this out from its electron configuration, and it has the same electron configuration as neon, which means it can act now like a noble gas and be more stable. Now let's get back to notes. All right, when we're talking about positive ion formation, we're talking about metal ions. These are the most reactive because they want to lose valence electrons. And the most reactive metals are groups number 1 and 2, the alkali metals and the alkaline earth. However, groups 1, 2, and 13 are metals that form positive ions. Now, if you look at group 13, it starts with boron. So boron's a semiconductor. It's not necessarily a metal, but the metals in groups 13 can form those positive ions. Now, transition metal ions are a little bit different. The reason we call them transition metal ions is because their charges continually to change. Now, these are going to form positive ions with a 2+ or a 3+ charge. Sometimes they will do a 1+ charge. That's just not as likely as 2 or 3+. Now, let's look at negative ion formation. Nonmetals easily gain electrons to attain a stable outer electron configuration. So they want to take in electrons so that they can get happy and have that 8 on their outer layer. Negative ions are called anions. And to designate that something is an anion, the ending of the name is changed to IDE. So for example, chlorine, once it becomes a negative ion, we call it chloride. So what would we call nitrogen? I'd like you to write this down in your notes and pause the video while you write it down, and then we'll check for your answers. All right, nitrogen is going to become nitride, Nitride. Now let's look at an example of a negative ion forming. All right, so let's look at one of our nonmetals. One of our nonmetals, let's see, would be, let's do chlorine. Chlorine has an electron configuration of 1s squared, 2s squared, 2p6, 3s squared, 3p5, right? Now, let's look at argon, because argon is the noble gas right next to chlorine. Its electron configuration is 1s squared, 2s squared, 2p6, 3s squared, 3p6. Now, remember, on chlorine, your valence electrons for chlorine are 7. So these right here that are circled represent the 3rd energy level because it has 3 right here. And chlorine's Bohr model is going to have 3 energy levels. So that means 7 electrons are on the outer energy level because you're going to add those together to equal to 7. Or you can draw the Bohr model if that helps you better. Now, once we add, since it's got 7 on its outer layer, it just needs 1 to be happy. And it would rather try to find 1 than try to lose those 7. Okay? So once it finds that extra electron to take in, this is going to change to 3p6. And if you'll notice, the electron configuration now matches argon. Again, chlorine does not turn into argon. It just takes on its electron configuration, so it's able to act stable and act like a noble gas. All right, so we've been talking about negative ion formation. They're done between nonmetals make negative ions. And so nonmetals always want to gain the number of electrons that, when they're added to the valence electrons they already have, that number then equals 8. So if they have 7 valence electrons, they want 1. If they have 6 valence electrons, they want 2. So an example, fluorine has 7 valence electrons. It gains 1 electron to get a stable outer energy level of 8. And this makes the fluoride ion, which is F negative. Sulfur has 6 valence electrons. That means it needs to gain 2 electrons to become stable. And this, once it does that, it makes a sulfide ion, which gives us S2 negative. Now, these charges right here that you see are always how many electrons they've taken in. So if we have a fluorine ion that needs to take in 1 electron, it's going to give it a -1 charge because electrons are negative. So that if you take in 1 electron, 1 negative charge, your charge is going to be 1 negative. If you're taking in 2 electrons, 2 negative charges, your charge is going to be -2. So let's, for example, what if we did magnesium? Magnesium has, well, let's look at it. All right, so let's look at magnesium right here. Has 2 valence electrons, okay? So once it gives those electrons away, I'll show you. 1, 2, oop, I drew that one a little rough. 4, 5, 6, so that makes 10, and it has 12 total, so we have 1 and 2. Now, once it gives these 2 electrons away to something else, that means it lost 2 electrons, so it now has a +2 charge, okay? Lithium has 1 valence electron, so it gives that 1 electron away and has a 1+ charge. So for positive ions, however many electrons they give away, that's the charge number. For negative ions, however many they take in is the charge number. All right, that concludes today's video. And what I'd like to do is I'd like you to write a summary of the video. I want you to write the 4 most important points you think we talked about in the video. And I'll see you in class.